So here's an old BC only problem. It's from the 2015 exam. It's a non-calculator question. Setup here is they give us this function that has this unknown constant k within it. The derivative of the function they were nice enough to provide us with. Ignore all these arrows for a few seconds, but they already computed f prime for us. If you look at part A, what they tell us is they tell us that k is going to equal 3. So that our function looks like this, right? So they just put 3 in place of that k for us, so that was kind of nice. Write an equation for the line tangent to the graph of this function at the point whose x-coordinate is 4. So you're building the equation of a tangent line. Anytime you're building the equation of a tangent line, you need two things: the slope of it and the point of tangency. The slope of the tangent line is, of course, going to come from the value of the derivative at the x-coordinate for the point of tangency. So all these arrows here are just kind of my way of reminding myself that I needed to put 3 in place of these k's, and I needed to put 4 in place of the x's. So you basically have to replace 5 things within this derivative, and just make sure you're replacing each of those constants or variables with the appropriate value. And if you do that successfully, you end up with this expression for your slope. For the point of tangency, you know the x-coordinate is 4. You need to find the y-coordinate that goes with it, so you're tossing 4 into the function in order to find that. So if you evaluate this function at the x of 4, you end up with this. So I have two different answers down here at the bottom of my screen. I have this answer that would receive full credit on an AP exam, because as long as your answer depends on numerical values, even if they're not simplified, if those numerical values are correct, you're going to get full credit. So on an AP grading style, this right here would receive full credit, but I'm sure a lot of teachers and professors are going to ask you to clean that up a little bit. So if you do evaluate this or simplify this and simplify this, here's a nicer looking answer that a teacher or a professor might be asking you to build toward. Part B gives us a new value of k. So now k is supposed to be 4, so here's what the function looks like when that happens. We're asked to determine whether the function has a relative min, relative max, or neither at the x value of 2, and then as always justify that answer. So if x equals 2 is the location of a max or a min, then one of two things has to happen at that x value when we plug it into the derivative. Either f prime of 2 has to equal 0, we have to have a horizontal tangent at that location to have a max or a min, or we could have a cusp, an undefined slope at that max or min. So 2 has to be a critical number. And so I was just trying to confirm that really quickly, so I put 2 into the derivative, and like we talked about in part A, I did have to put 4 in place of these k's, so make sure you're putting the appropriate value in place of the appropriate item in that derivative. And if you do that properly, you end up with 0 over 16. So yeah, f prime of 2 is 0. So we can't say neither just by this calculation. This means that we still have to investigate a little bit further. All it tells us that, yeah, 2 is the potential location of a max or a min. If we want to confirm what we have there, we would want to build a little sign chart. Now, the thing you have to be really careful about with regard to this sign chart is that although we're mainly concerned with the x value of 2, we do need to know where else the derivative has the potential to change signs. And so the only time that this derivative, when k is 4, is equal to 0 is when x is 2. But if you look at this denominator, if you factor in this quantity here, you're going to be able to pull out a common factor of x, and you're going to have x times x minus k. Well, if k is 4, that's x minus 4. So the derivative is undefined at 0, and the derivative is undefined at 4. So what I wanted to do is I didn't want to go to the other side of this x value or to the other side of this x value with the test values I was using to figure out what the sign of my derivative was, because these are also locations where the derivative has the potential to change signs. We don't really need to worry about what's going on over here or over here, because we're only concerned with the x value of 2, but we do just have to kind of double check that we don't extend over to 5 and use 5 as the sign. Whatever the value of the derivative is at 5, we don't use that as the sign of the derivative here. It might be the same, but then again, the derivative might change signs as we cross this location where the derivative and then also the function is undefined at 4. But if you test the sign of the derivative on either side of 2, you get a positive to the left and a negative to the right. That does tell us we have a max at 2, but as I'm sure as you've been prepping for the AP exam, you've heard, When you justify, you can't let the sign chart be that justification. So just kind of verbalize what the sign chart tells you. So f prime changes from positive to negative as we pass through the x value of 2. Therefore, we have a relative max at 2. Third part here, find the value of k where f has a critical point at the x coordinate of -5. So one of two things has to happen at -5 in order to make it a critical point. Either the derivative has to equal 0 there, or the derivative has to be undefined there. A rational function, a function that's a polynomial over a polynomial, it's going to be undefined anywhere where the denominator is 0, and that's also where the derivative is going to be undefined. A rational function is not going to have any cusps or anything. Since the function is not going to be undefined at -5, we can kind of rule this out as a possibility, but in general, you'd have to worry about the derivative being undefined at a value as a potential location for a critical point. But in this case, we just really need to worry about setting the derivative equal to 0. And so if we set the derivative equal to 0 with this x value tossed in, we end up with this expression here. And this expression is going to equal 0 only when the numerator is 0 and the denominator is not. So I set the numerator equal to 0. I got -10. I did do a quick double check. Is my denominator also 0 if this is my value of k? It's definitely not. 25 plus -50 and then square it. Yeah, that's not going to be 0. So the derivative is 0 at this x when k is equal to -10. Short and sweet there in part C. And then the last part of this is the lengthiest part. This is the BC only portion of the problem. So this question was split between the first 3 parts being AB content and now this part being BC content. We're asked to do a partial fraction decomposition for the function f when k is equal to 6, and then we're also asked to find the antiderivative of that version of f of x. So when you do a partial fraction decomposition, what you want to do is you want to have the denominator in a factored form. And so when you factor this denominator, it's a quick GCF that comes out after you put, well, they've already done it for us, but after you put 6 in for k. And then when you decompose this into its partial fractions, these are distinct linear factors, and that's the only partial fraction decomposition you're going to be asked to do on an AP exam. A teacher or a college professor would probably be expecting other partial fraction decompositions to be able to be carried out, but for the purposes of the AP exam, this is the only one we have to worry about. Anytime we have linear factors in this denominator and they're different from each other, all we're going to do is we're going to take a constant over the first linear factor and we're going to add on a different constant over the second linear factor. If you find a common denominator between these two denominators, it takes us back to this product. So I basically have to multiply this numerator and denominator by x minus 6 to build to this common denominator right here. Similarly, I have to multiply this numerator and denominator by x in order to build to this common denominator. So a is going to have to get multiplied by the opposite denominator. B is going to have to get multiplied by the opposite denominator. This is still equivalent to what we had over on the previous left-hand side of the equation. And at this point, if you multiply both sides by the denominator goes away. So you're left looking at this. Now this is kind of a weird situation, but whenever you carry out a partial fraction decomposition, you're using a process that's called equating coefficients. So if you look over here on the left-hand side of the equation, there is no x. So the coefficient of x over here is 0, and then the coefficients of the x's over here are a and b. So 0 has to be equal to a plus b. And then if we equate the constants on the left-hand side of the equation with the constants from the right, the constant on the left is 1, and there's only one constant term on the right that doesn't depend on x, it's negative 6a, and that actually lets us find a right away. And then if we take that value of a and substitute it right here, we get b pretty quickly as well. So we get negative 1/6 for a and positive 1/6 for b. So if I put negative 1/6 here and I put positive 1/6 here, but then I think about trying to find my antiderivative, my indefinite integral of f of x, the easiest thing to do is to factor that a out in front of that integral, factor the b value out in front of that integral. The antiderivative of 1 over x with respect to x is natural log of the absolute value of x. We just have to make sure we account for that coefficient that we factored out a few seconds ago. Technically, I would would need to do a u substitution here, let u equal the denominator. But my derivative is going to be 1, so I don't have any cancellation that needs to happen. I don't have any new factors that sneak in after doing that substitution since the derivative is equal to 1. And so I get a similar looking antiderivative here multiplied by this. And then you can try to simplify that with some factoring and some properties of logarithms, or you can just leave your answer like that.